Hello, everybody. Welcome back to another Strengths Materials video. This one is super easy. We're talking about force resultants here, and we're following some super easy rules. And this problem is pretty straightforward. It's just asking us to figure out what the single resultant force would be for a beam assembly like so. We have three different loads applied. Two of them are diagonally applied, and we have a moment externally applied at the end as well. And it's asking us to determine what resultant force would be equivalent to all of these forces acting on this beam. So, in order to do this, we need to do a couple things. We first need to identify, what are the different components of this resultant force. So, since we have some diagonally applied forces here, we're going to have x components and y components that are created. And in turn, that's going to mean that our resultant force is also going to have some type of inclination as well, based on that. And then the location of where that's going to be acting, it's wanting us to reference with respect to B. So we'll see later on the problem how that is going to change some of our calculations for our final answer. But pretty much all it's asking us is where is this resultant force going to end up on this beam with respect to this point, this roller. So the first thing we should do is identify what components we actually have in this problem, because we can't necessarily work with these diagonals right away until we break down these components into x and y variables. Okay, so now we have a little bit of a clear idea of what we need to do with these diagonal force components, because we've now broken them down into x and y components individually, which allows us to work with our previous equations, such as the summation of forces of x and the summation of forces at y. Why is this important? This is important because we need to figure out the summation of each of these individual variables in order to figure out what the total magnitude of that resultant force is going to end up being. And you're going to see what I mean in a little bit. But the first thing we need to do is figure out what the summation of forces in the x direction are and the summation of forces in the y direction. So if we start with x first, we can say that the summation of forces at x is going to be equivalent or equal to the resultant force in the x direction. And our convention will be positive to the right. So if we try and solve for the resultant force in the x direction, we can start figuring out which forces to use, which are these blue ones that I've drawn here. And what are these equivalent to? Well, we know based on this abbreviation I've drawn at the top, it's SOHCAHTOA. It's super simple stuff. We're just figuring out what this component would be based on the given information. So we have a 60-degree angle. This 450 will be acting as our hypotenuse, and we're looking for the adjacent force here, meaning that in order to solve this, we have to take 450 and take the cos of 60 degrees. And then very similar thing on this side, except now we have a 700 Newton hypotenuse. We're looking for the opposite. If you imagine this blue force closing the triangle up top here, we're going to have this on the opposite side with respect to this 30-degree. So that's going to end up being negative because it's acting to the left based on the way this diagonal is acting right now. We have negative 700, and that's going to be sine 30. That's going to leave you with a resultant force in the x direction of negative 125 newtons. Therefore, that means that the force is going to be acting to the left based on our convention. And we can do a very similar thing with the summation of forces at y. Taking the summation of all of these y components and y forces, we're going to be able to figure out what the resultant force is, its y component, uh, and then use this later on for the total magnitude. But the y component for the resultant force is going to look something like this. Very similar thing. Now we have 60 degrees. If you imagine the red force is closing the triangle on this side, we're looking at the opposite with respect to that 60 degree. It's going to be taking negative 450 based on the sign convention, sorry. Positive would be upwards. So this is acting downwards right now. So we have negative 450, and we're taking sine of 60 degrees. Have to consider this 300 right here. That's simply negative 300. Then we also have this 700 here as well. That's going to be negative 700. And we're taking this 30 degree. We're looking for this component here that is adjacent with respect to the angle, meaning that we're going to be taking the cosine of 30 degrees. And then solving for this, you're left with a resultant y component of negative 1296 newtons. And in order to get the total magnitude of this resultant force, we're going to have to take the component of Fr at x and Fr at y and simply use what? We're using Pythagoras' theorem. So if you had a squared plus b squared is equal to c squared, and you isolate for c, you can be left with a formula that looks like this. And that is going to be giving you the total magnitude of that force, where a and b is equal to x and y respectively. So if we replace this for simply Fr, that magnitude is going to equal to Fr at x squared plus Fr at y squared. We can simply plug in the numbers that we just solved for here. So we have for the x component, we have negative 125. Negative's not going to matter since we're squaring it at the end of the day. And the 1296 is also squared for the y component. And solving for this, you're left with 1,302 newtons. That's going to be your magnitude for this resultant force. But there's also another important consideration that we need to consider for this resultant is now what is the angle that's being created by this resultant force. So if this was Fr, we know that we have, sorry, but these lines aren't super straight. We have a really large Fy component and a very small Fx component, meaning that the angle being created is going to be right in between this reference point. And in order to solve for that angle, we have to consider what these forces are doing. So if we imagine that this Fr at y was closing the triangle on this side, we can take the tan inverse with the opposite over the adjacent in order to figure out what that angle is to figure out what the inclination is for that resultant force. So if we took tan inverse of the Fry, which was solved for here, that's 1296, you put that over the Frx component, which is 125, that's going to allow you to solve for theta. And theta simply equal to 84.5 degrees. So these are some of your important variables that we're going to be taking forward for the next part of this problem. Okay, so now we cleaned up the problem here, and I've added a point where I think Fr is going to be acting on our beam. And there's some important takeaways that I wanted to point out before jumping into the rest of the solve. And pretty much the one thing that's going to jump out to you guys is that we have an x here that's going from A to the resultant assumed location. But the problem is asking for the distance from B to Fr. Now, why do I need to consider this x from A to Fr? And it's for simplicity mainly. If I took a moment above B, for example, and I'm saying moment is force times distance, right? If we're looking for this distance between B and the resultant, then we need to consider a moment equation. However, if I took Fr about this side, the sign convention is going to be different than if I took it from the other side, because we know that the convention for moment typically is negative for clockwise, positive counterclockwise. So depending on which side you're taking, and if your reference is B, your signs are going to be a little bit weird. So it's easier to take it about A, and then you can guarantee that your resultant force is going to be creating a negative clockwise rotation. Some other important points, we're going to be just looking at the y components for the moment. So what that means is that we're pretty much assuming that this beam's thickness is negligible. Just felt like pointing that out. It's really not too big of a deal, but for the sake of accuracy in this problem, we're just neglecting these x components in moment calculations. Um, and yeah, we can pretty much go right ahead and say if our summation of moment about A is equal to the resultant moment at A, that resultant moment has to be equal to the resultant force Y times the distance away from A, which is currently labeled as x. So let's solve for what that is. Fry has been solved for already, and that's going to be a downwards force, meaning that it is clockwise rotation, meaning that this should be negative 1296 at a distance x. And then this resultant force times x should be equal to all of the external moments produced by the forces and external moments applied. So we're simply going from left to right and considering all of these different external forces. So let's see what that looks like here. The 450 first, creating a clockwise rotation. All of these are going to be creating clockwise rotations, by the way. So if you are confused by the sign, that is why I'm just brushing over it. They're all going to be negative. So we have 450 sine 60. And then that distance is going to be 2 meters away from A. We have the 300, which is 2 plus 4, which is 6 meters away. Then we have the 700 here, not considering the resultant because we already have it considered right here. Go right to the 700. We have negative 700. And that's going to be cos 30. We've already figured out what those components were in our previous steps. That's going to be 2 plus 4 plus 3. It's going to be 9 meters away from the support A. And we lastly have the external moment in the clockwise direction as 1,500. And then bringing this over, solving for x, you're going to be left with 7.36 meters. But if you wanted x with respect to point B, you just need to take away 6 meters. So 6 taken away from 7.36 is going to be 1.36 meters. Those are pretty much your final answers for this problem. I hope it helped. It's a little bit confusing if you're not used to solving problems like this, but once you get the hang of the trigonometry aspect, I think that's kind of the main one that kind of trips people up. But other than that, it's pretty straightforward stuff. And if you have any questions, please let me know. Thanks.